So let's just start now. All right. I hope everybody can see my screen. I'm Jean Favre. I'm the, I guess I can say the specialist of ParaView at CSCS. I've used the application for many years now. And I'm quite excited about sharing my experience with it. Now, yes, ParaView is a very mature 3D parallel visualization system in use at CSCS among other tools for many years. And usually people create a client-server connections so that they can visualize their data directly from the Scratch file system of Daint. But that is sometimes a bit complicated. And of course, it requires that you have quite a bit of master experience with this client-server connection. Now, ParaView, if you use it as a desktop application, has a very nice graphical user interface, which allows you to do a lot of trial of different visualization scenarios. But the very interesting thing about ParaView is that it also has a Python interface. So once you have a visualization which you like, which you'd like to share, or which you would like to reproduce, the absolute best way is to use the Python interface. ParaView has actually another option when you want to save your visualization. You can save a so-called state, but that state file is actually very difficult to edit. Yes, it's ASCII readable, but there's really very little you can do besides replaying it without any modification. So using the Python interface instead is a lot more versatile, a lot more efficient and productive way of using ParaView. There. Now, going to the Jupyter notebook side, we're going to be able to execute in standalone mode or connected to a ParaView parallel server the same Python script which your desktop application could execute. When I say the same, it's not 100% the same Python script, and that's what we're going to see this morning. There are a few tweaks to do from an existing Python script to be able to run in Jupyter. Okay. All right, so I've mentioned, yes, that sometimes the connection process from the desktop ParaView to Daint via SSH tunnels, etc., can be a bit complicated. And the users who have interacted with me in the past, I think most of them, the very first hurdle was to actually connect via a remote connection to Daint. So this is all something we get rid of using the Jupyter notebook, because we have directly from the web interface our connection to Daint. If, as Tim mentioned to you earlier this morning, if you have a GPU allocation, you can of course use the GPU to do rendering of your ParaView script directly in the Jupyter notebook. Otherwise, if you have a multi-core allocation, you can also do rendering with a method called off-screen software rendering, and the performance is actually very good. So you should not be slowed down by the fact that you do not have an allocation on the GPU. So the things we're going to see this morning is actually the hello world of ParaView, which I've called Hello Sphere, how to display a single sphere, because that's the very first test people do even with their desktop, how to display a three-dimensional sphere on the screen. And then we'll go about how to augment that with IPy widgets. We'll see how to do this in parallel. And then something that is very important is actually how to read your own data into ParaView. Now, like most, like I should say, all visualization application, there are a multitude of file formats which are already supported. Okay, so the very first way to ingest your data would be to use a supported file, as is being published in the ParaView web interface. However, if that fails, and if, for example, most of you presumably are using some type of NumPy processing or Dask or X-arrays, as has been mentioned already this morning, you'd like to be able to read those arrays directly into ParaView. So we're going to see how the different grid structures are born in ParaView, and I'm going to propose an interface to ParaView, which is a work in progress, which is something I encourage all of you to use. Report to me, contribute maybe some additional features, and we're going to see that in the so-called NumPy to ParaView chapter. And then, of course, Daint is a very large supercomputer system, and parallelism should be one of the driving efforts towards all of your computations. So ParaView supports very nicely two modes of parallelism. One of them is SMP parallelism on the node, and that will fit very nicely on a Jupyter notebook on a local allocation. And then we're also going to see how to do MPI parallelism by spawning an additional parallel task of ParaView of the so-called PV server, which is the parallel server for ParaView. So all of this is going to be between this morning, then we're going to have the lunch break, and then the parallelism demonstrations will be done after we come back from our lunch break. All right, prerequisites. So independent of the fact that you have an hybrid allocation, or hybrid, which is also the so-called EGL version of ParaView on Daint. This is the version of ParaView dedicated to running on the GPU. So there's a little typographic error here on my title. I wanted to say, independent of the fact that you have a multi-core allocation or an hybrid allocation, what you need to do in your .jupyterhub.env file, you simply load the ParaView module. And at this point in time, we have a single version of ParaView, so the default is the version that is being loaded, and it's version 5.9. Then for all the other details about how to set up the Jupyter Lab notebooks, the presentation by Tim this morning really had a lot of details, so I'd refer people to those details earlier in the presentation. Now, most of the notebooks I'm going to demonstrate are on the Daint file system in that particular location. All of my projects at CSCS are readable by everybody who has an account at CSCS, so you should have no problem changing directory to this particular folder. So we're going to look at our first Hello World program, as I had anticipated earlier. So basically, this pipeline is going to be made of three different set of objects. The standard ParaView Python initialization. Then there will be what we call in visualization language, usually we call this the visualization pipeline. So it's a set of data sources, a set of filters, and a set of representations which are then rendered on the screen to make an image. And to do this rendering on the screen, this will be the little trick that we need to put on the standard ParaView Python scripts. We're going to use a so-called PV Display widget, which is something that was contributed by NVIDIA. So on the right side of my screen here, I see those different steps. The initialization is the standard from ParaView.simple import star. So the whole ParaView ecosystem is loaded into our Python world. And then the sphere function here is a module that serves really to generate the geometry of a simple sphere. We have two arguments which we give here in this particular example, the theta resolution, which would be the longitude, and then the phi resolution, which would be the latitude of that sphere. And then the special keyword for any object in a ParaView pipeline, that special function is show, which creates the so-called representations, which are the graphical objects which need to be rendered to make an image. So for each object in a ParaView pipeline, if we want to make it visible, we're going to show it. Now, that might seem something obvious, but it turns out that ParaView is not only about making images. There's a lot of data filtering, data processing, feature tracking, for example, which does not need to be seen on the screen. So this is also something that perhaps the beginners here with ParaView need to remember. ParaView is not only a graphical interface to data, but it's a generic data processing application which runs also by default or in a transparent way, I should say, which runs in parallel if you have very large data. Now back to our sphere object here. One of the representation mode is to show it as a surface with edges. So this is what we see on the screen here. We see a very bland spherical object with its wireframe representation superimposed. And to make all of this possible and to make it visible, we use this PV Display method from the ParaView module, which was contributed by NVIDIA. So I'm going to switch screen for a minute, and we're going to go directly to my Jupyter notebook to demonstrate this particular first example. So give me a second. I will switch. I will share screen now on my first desktop here, and I have my example here, the ParaView Hello World test. So very first cell to execute is this, the import statement for the whole ParaView package. And it's called simple, but as you can see, it's actually taking quite a few seconds to load because there's a lot. ParaView is a very large package, actually. If one would want to make this initialization faster, we could actually import just some specific packages. But for simplicity here, we import everything. Then we make our sphere object, okay? And as you can see, for the moment, there's nothing happening. There's nothing being displayed because we haven't executed the display operation. So we create a default view, and that view, if I recall correctly, will have a size of 400 pixels by 400 pixels. And then the magic happens when we execute this ParaView widget, command, and here we have a live object. As you can see, I can move around my object, zoom, etc. There. So we have our first live visualization with ParaView using a very simple Python script. Now, if I want, of course, we've lost the desktop graphical user interface. And the desktop, for those of you who have used the desktop application, you know that there are hundreds, literally hundreds of different switches, different options to execute filters, to change the representation of the view. So it's kind of difficult to. And here, I'm not trying to teach you how to use ParaView in 30 minutes. We're going to do some things very simple. So this object, which I have called rep, has a particular representation, okay, which was set earlier in cell number 3. And if I change that to ask what are the representations available, I have here a list of representations which are possible. So should I want to remove the wireframe representation, I would simply switch to the surface mode, and there is my sphere. Of course, it's a spherical object, so even if I rotate it, it makes it difficult to view the object. I can do the same thing, changing my representation here to wireframe without the typographic error. And there is my object again in wireframe mode. All right. So that's all there is to it, basically. We can execute a Python ParaView script directly in the Jupyter notebook. Now, your first question should be, okay, I have a desktop application. How should I go from the desktop version to the Jupyter Hub version? So I have made here the same example this morning, which is this Python script, which the desktop application created for me. And we're going to look at just a few of those lines of code here. This is quite detailed, but we have here the from ParaView import statement. We have here the create view statement with a different view size. Okay, that's fine. Here, the layout is something we can skip. Here's the definition of the sphere object. And here we use the default sphere object, which means that it has a resolution of 8 by 8 in the longitude and the latitude direction. And then here again, we have the magic show command to create a representation of the sphere to be displayed. So that is what is important for us. The representation type is over here. And since there is, at the moment, there's no scalar field or vector field attached to the sphere, we cannot color, we cannot pseudo color the geometry with a particular field. So the color array name is set to none. And basically, that's about all we need here. All of those other details are not so important to make your first Jupyter Hub program. So we're gonna do this exercise here. I'm going to create a Python 3 notebook over here and start with a blank page. Now, just to make things a little bit faster, I'm going to cut and paste from my desktop ParaView Python code into the Jupyter notebook. So there's my first cell. The second thing I need is the creation of a view. So all I need really is about 2 lines of code here to create my view. Now, notice that when I create a view, nothing shows up on the screen actually, because you have to remember that the rendering is done off screen, meaning without a physical screen. It's done either with software rendering or on the so-called embedded GL version of ParaView. But everything is fine for the moment. Then we need the magic 3 lines here. Actually, even 2 lines are enough to create a representation of the sphere. There it is. Yeah, I simply forgot to create my object. So let's split the cell. I went a little bit too fast, and there is the object that I forgot to create. So first, create an object, and then display it. There we go. We're back on our feet. And the last command we need is to actually display make that image. And for this, we go to those 3 lines of magic from the IPy ParaView widgets, import the PV display. And there is, again, our sphere. So you've seen how we've moved from the desktop Python script to the Jupyter Notebook version. Now, my sphere object over here, of course, has a particular data resolution of 8. Like I told you, this is the default. We can change that to any number. And as you can see, I have now a more defined object there. So that's about all there is to migrating from the Python script written by the desktop application to the Jupyter world. So what is important to remember is that we create a view, we create an independent view over here, and then we make a physical instance of the representation with those 3 lines of Python code. Let's see, I wonder if there are already some questions which I've missed. I need to be alerted of. Somebody is asking if the slides are online. They will be available as soon as, perhaps during the lunch break, because I had a little problem making them available for everybody. Somebody missed the initialization of ParaView, so I'm going to show that very briefly again. I'll switch back to my presentation over here. And in my prerequisite here, this is what you have to do. Module load ParaView, and that command is put into your file .jupyterhub.env. And with this, you should be able to replay the exercise and follow along. So the resources are, all those notebooks are in that following location on Pitts Daint. That's my username, the projects directory, visualization, training, and then. All right, so we've done our first example here with the demonstrations on how we could go from the desktop version of ParaView to a Jupyter Hub version. Now, as you can see on the image here, this is a screenshot of my complete desktop application. Here, for the data resolution, for example, and the file resolution, I have a couple of widgets, interaction widgets for me to change, and I can also change the initial phi and end values. Here the defaults are 0 to 180 degrees. For the longitude, I have a default between 0 and 360. So how can I replicate, or at least take a subset of those graphical user interface widgets from the desktop application and put them into my Jupyter notebook? It's actually pretty simple. I want to show you, I want to highlight one thing, by the way, here. On the desktop version of ParaView, there's a special setting which you can use, which shows here with little arrows that this parameter can be animated. So not all parameters can be animated, but for some of those, as you can see here with these little green arrows, it is possible to animate. So we're going to see how this is done. For any object in a ParaView pipeline, that object, for example, the sphere here, that object responds to a command which can list its properties. And those are the properties that can be animated. If I do this in my Jupyter notebook, you will see that I get a list of strings, okay? For example, the center, which would be a tuple of 3 floating point numbers. For example, the resolution, etc. The radius, which would be a floating point number. Those elements here can be modified via the graphical user interface. So what I'm going to use is attach, for the example here, attach the phi resolution and the theta resolution to an integer slider. Tim has introduced that this morning, showing you how we can use the IPy widgets, the IPy widgets to do very simple animated widgets. So in our case, we need to define a callback function, and that callback function will be called sphere resolution. It takes one argument, the resolution here, which I have written as a 3-letter word. And when I change my slider, we're going to see the live version soon. When I change the slider, I update both the phi resolution and the theta resolution. And then there's a special keyword, a special method for all ParaView objects, which is called update pipeline. This triggers actually the re-execution of the pipeline. The reason for this update pipeline is that sometimes if the data are very large and there's multiple changes that we want to apply on the pipeline, it's better to buffer all those different changes and then at once trigger the update. So this is what this is all about. So this is what our interface is going to look like. We're going to have here our slider. If you follow my mouse here at the bottom of the screen, this is the code, the definition of our callback, and then the interact function. I'm going to switch again screens so that we see that live on my other desktop. There we go. So this was our first example. I will get rid of this. I will get rid of this, close this, and I will go to Hello Sphere ParaView 1. Here I import my ParaView. I've added here some other codes for you to see that we are effectively running on the GPU hardware for this particular allocation. So this is the Tesla P100 GPU on the compute node of Daint. we create our sphere object, we create our view. There's our view. It's already a live view. But at this point, I'm going to go to cell number 6, import the integer slider and the interact method from IPyWidgets, set up my callback, and let's see, I have, oh, there we go. Sorry about that. So there we go. I now have a live slider. And as you can see in the view above, I'm updating the visualization, the resolution of my object. The next cell here is actually one of the caveats, one of the problems we currently have with this implementation of the NVIDIA widget to display images. The standard save screenshot of ParaView does not work anymore. So I've replaced it with this particular version, and I am now in discussion with the NVIDIA developer to try to resolve that bug. But for the time being, you can very safely use this particular method here. And as you save images here, you can give it a path name on the Daint file system. There. So this is about all there is to the demonstration of how we can attach IPyWidgets to the ParaView objects, which can be animated. In this particular case here, remember, sphere list properties gives us a list of all the objects, all the methods that can be changed on that particular object. I'm going to go to version 2 of the test here, the Hello World test. And this one is about running ParaView in parallel. So far, over here, the version 1 of my Hello World program, we have a single task creating this visualization pipeline and participating in the making of the image. Now, this is to whet your appetite, because we're going to see this after the lunch break, how to actually launch a very large parallel visualization software, a parallel visualization session. Let me get a terminal, which I'm going to run here on the side. So I am on the compute node. My module, my ParaView module has already been loaded, but just to make sure I can do this. And I can see that I have an object called, an executable called PV server. This is the parallel version of the server. When I run a standard desktop application of ParaView or a standard Jupyter Lab notebook with ParaView, there is an integrated ParaView server into the execution model. So I don't have to do anything in particular, and I run with a single task. If, however, I'd like to run with multiple MPI tasks, this is what I would have to do. And let's run, for example, with 8 tasks of the ParaView server. So I'm still running on one compute node here, but I have 8 MPI tasks of the ParaView server waiting for connection. And because my Jupyter page here runs on the same compute node, what I have to do, this is my cell number 2 here, I connect to myself. In other words, I connect to the local host. So there we go. You've seen that on the right side here, the message client connected has appeared. Now it takes, with the current version of ParaView, which is 5.9.0, we actually have quite a bit of time between the actual message client connected. And as you can see here, that cell number 2 just finished executing. So you have to be patient. I'm hoping this will be resolved in version 5.9.1. I'm going to interrogate the ParaView process to see how many ranks and what is the information of the render, the OpenGL renderer on this particular session. So as you can see here, I have printed the rank and the number of processors. So I have rank 0 out of 8 processors. Each one of them is running ParaView version 5.9, and it's effectively the parallel session I have here on the right side of my screen. Now from here on, nothing has changed. I can still create a sphere of resolution, in this case 32 by 32. And because the show command here involves the creation of the view with the get active view command, as you can see on the right side of my screen, the 8 MPI tasks of PV server have recognized the Tesla P100 GPU and are ready to do their rendering. So for those of you that are not familiar with how ParaView works in parallel, the data is actually subdivided among the different ParaView servers, and the compositing of the image is done transparently by the ParaView servers. So I do not have to do anything special to combine together the contribution of each GPU. And we're going to see this in a few seconds. So I'm going to get my PV display. And here what I have done, I have colored the geometry of the sphere. For each processor, I've used a different color. Okay? And this is done by this command called color by, the representation name, and the name of the scalar field. When I run in parallel, there's a special scalar field called process ID, which enables me to select, for example, the contribution of each processor. So I have here a live parallel visualization. The coloring represents the contribution of each processor. And I can go back to my IPy widgets over here. By default, the default was reset to value number 12. And as you can see, as I increase the resolution of my widget here, the contribution of each processor or each GPU augments. So if I go here to the maximum, I guess since I'm using 8 processors, it would be wise to use, if I set, for example, 36, I have exactly 36 slices along the longitudinal direction, which are distributed among 8 GPUs, which makes four slices of data, if you want, by processors. There we go. The save image is the same, which means that the save image will work in parallel. And then once I am done with this dedicated ParaView server, I simply disconnect from it. And as you see, when I disconnect, here on the right side of my screen, that particular S1 job has exited cleanly. Each GPU has been shut down. There we go. I'll switch for a moment back to my PowerPoint presentation to finish up. All right, so I've talked about the limitation of the save screenshot at the moment, which no longer works. So you'll have to create that particular definition for the save image, and then you can go on. Data interfaces, how to read your favorite data arrays. Now, what I have done is I have created a set of so-called grid constructors, which is an early attempt at reading in any types of NumPy arrays and creating the proper grid structures from the VTK world. Now, when you use a supported data format, you read your data, and ParaView automatically creates the proper grid structures which fits your data. So it can be a regular Cartesian grid. It can be a rectilinear grid. For example, this is used very much in climatology and meteorology. You can use a structured grid or so-called curvilinear grid. And there are a couple of cases of those curvilinear grids which are important. One of them is the spherical grid. The other one is the cylindrical grid. So I have made demonstrations of those, and I encourage you to, yes, use those grid constructors and then report any problem you have with them. So I'll switch again. Unfortunately, there's a lot of switching between screens here. I'll go back to my Jupyter page, and I'll go to the PV test grid constructors notebook. So the way to operate this particular class is to import it. So I simply here append to the syspath my particular ParaView Python directory, and I import the VTK grid constructors. And you'll see very quickly with the examples what can be done. So here's the example of a spherical grid. So I get here an empty blank page for the moment. I will execute. And to make things a little bit easier, I'm going to make a view, another view here, over here. And there's my grid. So I have a spherical grid of resolution 1, 2, 3, 4, 5 in the radial direction. And then I have, I forgot how many, but I'm going to look at the source code. There we go, 9 and 7 for the longitude and latitude directories. And then what is important to see from that example is that I'm using NumPy arrays. So for example, I've used the radius as a NumPy array, the theta and the phi scalar field to add to that particular grid. So the grid is constructed as a so-called structured grid or curvilinear. I give it the X, Y, and Z coordinates of each point on the grid. And then I can add any array I want, either at the nodes or at the center of the cells. This is an example which also demonstrates the support for cell arrays. So for this, I have simply reduced the resolution of my P array, which I still call phi, to make it a cell-centered scalar field. So there is the first example of our spherical grid. It's a bit complex because it uses the so-called programmable source. I don't have the time today to give you all the details about how do we program those programmable source. This would be the subject of the next dedicated courses on ParaView, which will take place in May. All right, I'm going to reset my camera, hide that particular object, and now go to the special case of the Cartesian grid, also called VTK image data. So here, we're going to look very quickly at the definition of the NumPy arrays. I select a dimensions, a cube of 64 cube, yeah. I select the physical bounds of the grids. I create an X, a Y, and a Z arrays for the three axes of my grid, and those are standard NumPy linspace definitions. I use the mesh grid functions from NumPy to create the three-dimensional X, Y, Z arrays, and then I make some artificial data, a scalar field, which is basically X to the power 2 plus Y to the power 2 plus Z to the power 2. And then from the VTK package included in ParaView, I import this image import from array particular function, which is going to facilitate the, I don't want to say the copying because it's a zero copy operation. In other words, we do not duplicate the NumPy arrays. We use the NumPy arrays directly as they are, and we basically simply add a link to the memory location from the NumPy space. So we create our image data. We set the scalar array associated with the vertices of that grid. We set the origin and the spacing of the grid, and then we update it. So as I execute this object here, we have now on the screen our 3D cube volumetric grid, and that's a Cartesian, that's a strictly linear Cartesian grid. The representation is set to surfaces with wireframe. If I switch that to surface, we can see here that we have the scalar field pseudo-colored on the representation of the geometry. I'm going to reset my camera, hide that particular object, and then create a cylindrical object. I think now you've basically understood how things work. I go from NumPy arrays to create a representation of the radial axis, the theta axis, and the elevation axis. So those are standard NumPy arrays. I create a mesh grid object for starting from those three different axes. And again, I instantiate a copy of a curvilinear grid. I set its coordinates, and then I add any scalar field, vector field, which I want to add to the to the object. So I'm going to execute this, and here I am coloring the object by the variable radius. And sure enough, you can see from blue to red here, I have a radius that has increased. I'll reset, I'll hide, and then I'll create one more object, which is a point cloud. I think sometimes people don't necessarily have a grid. They can also have just a set of unorganized points. And this is what we call a point cloud. So here I'm making 10,000 of those points. I forgot to remove the representation of my cylindrical grid, well, which somehow is stuck right there. Okay, never mind. So here's my point cloud here. Again, I have a set of random samples from NumPy. I have here a new function called VTK point set from arrays. I have two different ways of setting the coordinates of this point cloud, either by giving an X, a Y, and a Z coordinates as 1D NumPy array, or I can give it a full array of size n times 3 floating point numbers. So this is why we have here set coordinates from 3 different arrays, or set V coordinates with a vector of coordinates. Then I calculate a particular scalar field called the distance square, again by doing a standard NumPy operation on my arrays, and I add this to the point cloud. The final example I can show is the creation of a rectilinear grid. So the rectilinear grid has its own dedicated function here. Again, I give it an X, a Y, and a Z coordinate, and the rest is as usual for this example. The data is artificially computed as the square root of X plus Y plus Z squared. So that's the distance scalar field. And there is somehow my cylindrical array is getting in the way, but there is my rectilinear grid. As you can see, the resolution here varies. For example, in that direction here, along the direction of my mouse, the resolution varies as we go with the different grid indices. All right, in summary, this is a class I have constructed, okay, which is located in this particular directory. If you have NumPy array, Dask arrays, X arrays, you can bring that directly into ParaView using this particular method. So I have an example of this, which is over here, X arrays. I'm going to import a particular data set. You will recognize here my import statement. I read my data set with the standard methods provided by the XR package. I create my curvilinear grid. I add my temperature array, for example, in this case, and then the rest is standard ParaView visualization. So here's the print out of my X array data set with a particular latitude, longitude, and radius dimension. And as I color with temperature, we're going to see, here I'll go a little bit quickly, we're going to see our grid So this is a representation of the Earth gridded and the temperature within the interior of the Earth. And I've cut this particular grid in 3 quarters so that I could see inside the volume. This is the operation seen over here, extract subset, which is a standard ParaView, filter to do subsetting of grids. I'm going to quit here in a couple of minutes so that everybody can go to lunch. So I'll stop sharing this screen. I will, just a second here. Share that presentation to conclude with my first part. So we've talked about gridded data. We can also do molecular data. There's an example that you can try by yourself called Hello Molecule.ipy notebook. And that example is interesting because it's a time series of molecular trajectories. And I have attached an IPy widget to it so that you can animate that data. There we go. The example with the X-rays, we've seen it. And this is the notebook called X-rays ParaView Import Notebook. This afternoon, we're going to, after the break at 1 o'clock, we're going to see more of the parallel visualization scenarios which are possible with ParaView within the Jupyter Notebook. So I will stop sharing. I will verify if there are questions here that are pending. And otherwise, I wish everybody a good lunch and we'll come back at 1 o'clock for the rest of my presentation.